we're going to look at two theorems primarily. This section's not real long. The 4-7 that we're going to get into a little bit is quite a bit longer than this one. So the first thing I'm going to introduce you to is what Rolle's theorem is. Rolle's theorem is very easy to understand. What it's saying is a couple of things that are important. If the function's continuous on a closed interval and differentiable on that open interval, you're not going to be differentiable on the closed interval because those would be endpoints. Okay, so if the function evaluates as the same number, that's just saying same y value really. Okay, then it's going to say there is at least one point c that's in this interval such that the derivative is equal to 0. Okay, and the higher up you get into math, the more you got to read definitions and make sense of them, theorems and make sense of them. Visually, that's the way to make sense of this. So this diagram was what I put together to help you see this. So basically, here's your endpoints. You're looking at the closed interval AB like that. Okay, now is this function just by looking continuous? Yeah, is it always differentiable? Yeah, the derivative looks like it's always going to exist. So it turns out that there will be a point C, and the key thing is these 2 points have the same y value. So they have the same y value. So that means you're guaranteed to find some point, at least one point, you can find more than one, where the derivative is equal to 0. So in other words, you just have a slope of a tangent line that's equal to 0. Does that make sense? Okay, I'm going to do this again. I'll do another thing here. Let's say that this is A and B. Let's say that you have a point here and a point here. Remember, they have to be the same. Now, if I was to go through and make it continuous, how many points, on that example, would the derivative be 0? 3. Yeah, they're going to have a horizontal tangent line there, there, and there. Okay, so no matter how you draw that graph, okay, as long as it's continuous and differentiable, you're guaranteed to find one place where the derivative is equal to 0. You could even have this situation. You could have A and B. Remember, the y values have to be the same, and you could have a horizontal line. Okay, well, that would be an infinite number of places where the derivative is 0, right? Okay, so no matter how you draw that, you're guaranteed to get at least one point where the derivative is 0. Does that make any sense? Okay. Now it's got to be continuous and differentiable, because if it isn't, kind of the theorem falls apart, which I'll show you here in just a minute. Okay. So here's a couple of examples. Okay. Rolle's theorem requires continuity. Okay. So like for instance in this example, what you have is you have a closed interval AB. Would there be any place where the derivative is 0 in this example? You're not going to find any. Well, it's discontinuous. Okay, that throws out Rolle's theorem and it isn't going to work. Okay, now you might still be able to find a place on that on some of these situations, but you have to be continuous in order for you to have that situation happen. How about this one? You're not differentiable at that point because that's the sharp point or cusp. Is there any place on that interval where the derivative would be 0? Nope, so you're going to find it. Okay, so you got to be differentiable and you got to be continuous on that interval in order for Rolle's theorem to provide that one point, at least one point. Okay? Okay, so does that make sense, Rolle's theorem? Not too hard. Okay, we're going to do a little application on this and just do a couple things on the next page. So what we're going to look at is, okay, this is a polynomial. I went ahead and just graphed it because it'll help you visually see this. So if you graphed this polynomial on a graphing calculator, you're going to find 2 places where this thing is, where the derivative is going to be equal to 0. Now, before we even look at the graph, though, the first thing we're going to do is I'm giving you a function, and we're going to find an interval on which Rolle's theorem would apply to this. Okay, So what we're going to do is basically this. We need to go ahead and just factor this and set it equal to 0. So we're going to go ahead and let's start by factoring. How would you factor this polynomial? It has a common factor of x, so you want to take that out. So you're going to have x times x squared minus 7x plus 10 like that. Okay, then it looks like that trinomial is going to further factor. You're going to have x and x. 5 times 2 is going to give 10 with 2 minuses like that. Now remember what we're doing. In order for Rolle's theorem to work, this is kind of what you have to verify. Number 1, it's got to be continuous on an interval. Number 2, it's got to be differentiable. Number 3, you got to find A and B. You have 2 points A and B, but f of A has to be equal to f of B. That just means the 2 endpoints of that interval have to have the same y value. So what I'm going to do is I'm going to set this equal to 0. All right. Now what you're going to have then is you're going to have x equals 0, x minus 5 equals 0, and you don't have to write this down because you can solve all those equations in your head anyway. So what you get is x equals 0, x equals 5, and x equals 2. Okay, so you've got one number in the middle of that. So we're going to use these. That's the minimum, that's the maximum there. So what we're going to say is we're going to use the interval 0 to 5 to analyze Rolle's theorem, like that. So what you're really doing on that is you really found this. And if you look at the graph, and I went ahead and just did this graph for you, when x is equal to 0, what's the value of y based on this graph? Well, it's 0. So when we set that equal to 0, what we did is we guaranteed that we found a place where the y values are the same for these two things. So what we have on this basically is this. This is a polynomial function, so it's always continuous. There's no breaks in this function, right? Polynomials, college algebra, remember? Cubic does this. Always continuous, always differentiable. There's no sharp points, no breaks or anything in there. So we've kind of got that verified. We got that verified. And now f of 0 is equal to, you'd end up having that f of 0 is equal to 0. You would also have f of 5 equals 0. And you also have f of 2 equals 0. So you actually have 3 places that have the same y values. But let's just go all the way to the minimum of that and the maximum like that. Okay, so that's how I figure out 2 places, an interval that Rolle's theorem would work on. Does that make any sense? Okay. All right. Now, if we're going to do Rolle's theorem, what you need to do is you need to do the derivative. So we're going to go ahead and these, I guess, should have been g's. I wasn't paying attention to that. It was g of x is what that function was. Okay, so we're going to go ahead and do g prime of x, which is a simple polynomial. So that's going to be 3x squared minus 14x plus 10. So that's an easy derivative to do. Now, Rolle's theorem says find a value of x that's in the middle of this interval, 0 to 5, that has a derivative equal to 0. So what you're going to do now is you're going to set that derivative equal to 0, and then you're going to solve that equation. Okay? So everything okay so far with what I'm trying to show you? Okay? All right, well, let's solve this. Hopefully this factors. I don't know if this factors or not. If it not, we just got to deal with the quadratic formula. I think we probably have to use the quadratic formula on this one again. So 5 and 2, either way, that ain't going to work. Okay, bummer. We got to use the quadratic formula.
The quadratic formula is negative b plus or minus the square root.
All right, there. Negative b plus or minus square root of b squared minus 4ac. What's wrong with me? All over 2a. Write it down if you need to, because you're going to have to use it sometimes. Okay? Now we're just going to get decimals on this. So we're going to have b is going to be negative 14, c is going to be 10, a is going to be 3. So you can go ahead and just start plugging that in. So we have negative 14 plus or minus the square root of b squared, so that's negative 14 squared. 4ac, a is 3, C is 10. And it's all over 2 times 3, like that, okay? So let's see, that's going to be 14 plus or minus. 14 squared is 196, I think. That would be 12 times 10, 120 over 6. Now what I'm going to have you do on this is we're going to go ahead and simplify this. Let's just do that. So we got 14 plus or minus, that's the square root of 76 over 6. And then what you got to do on the 76 is you got to look and see if there's a factor that has a square root. And I think it divides by 4, so I'm going to just do that on the calculator real quick. I think it does anyway. So if I go 76 divided by 4, that's going to give 19. So I'm going to write this as 14 plus or minus 4 times 19 over 6. Then I'll write that as 14 plus or minus 2 radical 19 over 6 like that. Is that done? Now the thing that you got to do also on this is the part of the quadratic formula from background that sometimes students never got good, is those things all divide out. They all have a common factor. So the way I'm generally going to do this is factor a 2 out of the top. So I'd have 2 times 7 to get 14 plus or minus radical 19 all over 6. You have 2 times 7 is 14, 2 radical 19. Now you can reduce that 2/6 to a third. So what you would end up having then is you would end up having, as your answer, x equals 7 plus or minus root 19 all over 3, like that. So those would be 2 places that satisfy Rolle's theorem. And if you look at the graph that I provided here, that's what one of them is that x value. That 0.88 I put on there comes from the quadratic formula. Then the other one, 3.79, comes from the quadratic formula too. So if you just did, if you wanted to get a decimal answer on this, you would just go 7 plus square root of 19, and you can get an answer to that, and then divide by 3. And see, that gives the 3.79, so that gives that critical point. And then the other one, you would go 7 minus the square root of 19, get that answer, and then divide by 3, so that would be where you get the 0.88 like that. Okay? All right. So what's the hardest part of that problem? Quadratic formula, it's not that it's hard, it's just kind of a pain, isn't it? Okay, so it's kind of a pain to have to do that sometimes. But from time to time you have to do that. Typically on this, that would be the exact answer, but then you can use decimals to approximate if you want to like that. Okay, so do you guys see, really all I did on Rolle's theorem is I did the derivative, set it to 0, but I have to know an interval where that works. And the key thing on the interval is the y values have to be the same. The function has to be differentiable. These 2 endpoints of that interval have to have the same y value, and they do. Since it's continuous and differentiable on that interval, then Rolle's theorem applies. Does that make sense? Got to have those 3 conditions. Okay. Okay, let's look at this number 3 and see what we figure out on this. Okay, what you have is the function f of x equals absolute value of x. Now this is just an arbitrary interval. If it says negative a to a, that could, one example could be negative 3 to 3. Okay, it doesn't matter. So what does the graph of absolute value of x look like to you? It's like the V shape, right? Okay, and without going through all the details of this, you know, what you would find is the absolute value function looks like this. Okay, and then the points on this, like this would be a point 1, 1. This would be a point negative 1, 1, and then that would be a point 0, 0. So, why would Rolle's theorem not work on this problem? Good, it's not differentiable, okay? And remember, it's this interval right here, okay? Now it's got Rolle's theorem would work, and see the thing is the y values are the same right here. So you got 3 conditions. First condition is, are you continuous? Yeah, this function's always continuous. Second function is, the y values have to be the same, and they are, okay, from there to there. But the differentiability is what fails because of that cusp. So Rolle's theorem would not apply to this interval. Okay, does that make sense? Okay, so just get in your mind, you got to have continuity, differentiability, and what's the deal with the y values? Same y values, okay? That's the key. All right, any questions there? Okay, now we're going to go to, I'm going to move this next page, and we'll do a couple more things with Rolle's theorem. Then we'll take a break, and when we get back, we'll talk about mean value theorem. So let's go ahead and do these examples and finish these up. Okay, so I just took some things out of the textbook here. So you're given a function, and you're given an interval, and we're going to apply Rolle's theorem to this. So here's your function, there's your interval. So I tried to kind of give you a checklist, okay? And I did a graph just to kind of help you visualize this. So, and pretend like that graph's not there. Is this function continuous? Yes, how do you know? Well, it's really a polynomial. I mean, if you multiplied x minus 1 and squared it, multiplied by x, you get a polynomial. Is it differentiable? Okay, it's a polynomial. Polynomial functions are always continuous and differentiable. So you have to check that. Okay, you can look at your graph if you need to, but on a problem like that, you don't really need to. Now we need to figure out what f of 0 is and f of 1 is. And what are we trying to verify? What's the deal? What's got to happen to f of 0 and f of 1? They got to be the same, right? Okay, you can do this one in your head. F of 0 is equal to 0 times 0 minus 1 squared. That's 0, right? You plug in f of 1. That's going to be 1 times 1 minus 1 to the second. That's also 0, right? That arithmetic you can do in your head, I think, right? Okay, so Rolle's theorem does apply. What is Rolle's theorem going to tell us? That between 0 and 1, there's going to be at least one place where the derivative is equal to 0. I did this on the graphing calculator. You can clearly tell that right here, the derivative is going to be 0, right? Because you're going to end up having a tangent line in there that's going to be horizontal, okay? Now, what I'm going to do on this is we're going to do the derivative, and we can do this with product rule. We can multiply it out. It's kind of up to you. So I think what I'm going to do on this is just multiply it out. So I'm going to multiply out this x minus 1 squared. Now, you do what you have to as a student. You can write it out twice, or you can do it in your head. I kind of hope that calculus students can just do this whole thing in their head. So what are you doing? You're squaring the x. You square the negative 1 to get plus 1. Then you multiply the two terms to get negative 1x. Then you double it. Okay, so that gives minus 2x. Okay, it's very helpful if you get to a point where you can square binomials in your head regardless of what the situation is. Okay, now let's go ahead and multiply this out. So we're going to have x to the third minus 2x squared plus x is what f of x is. Okay? Now, if we're going to find that point where the derivative is 0, we're going to take the derivative. This is an easy derivative, so that's going to be 3x squared minus 4x plus 1, like that. And then we got to set that equal to 0 and solve. Okay, it's either going to be factorable or quadratic formula. So we got 0 equals 3x squared minus 4x plus 1. And let's see if this one, I think this one might factor. I think, yeah, I like that. Okay, that doesn't make sense though. Oh, I know what the deal's going to happen. Okay, so you're going to have minus there. So we're going to have this. Okay, so what you have going on this then is you've got 3x minus 1 equals 0. So that's 3x equals 1. So that's going to give x equals a third. So that looks like that's probably going to be what this point right here is. And then x minus 1 equals 0. You're going to get x equals 1. Okay. Now the thing on this one is you can kind of tell. You'd have to look at the graphing calculator to tell on that. So Rolle's theorem what you're looking for is strictly between. I'll come back to this page in just a second. I want to scroll up to Rolle's theorem and kind of read that off. Okay, so it says there is at least one point C in AB. Now notice that AB is open, right? So could you use 1 on this point, on this problem? No, not according to Rolle's theorem, because there's 1 point in AB, so it does not include endpoints. You might want to make yourself a note of that. Okay, so this one you would not use because it's an endpoint. We're looking at points strictly in between on Rolle's theorem. So the answer to the problem would be, right, x equals 1/3. Now this is, on my graph on here, this is 0, this is 1, this is right here is like 0.3. Okay, so it's right in there, it's right at that point right there. So that would be the solution to the problem. Okay, does that make sense? Okay, and the derivatives haven't been too bad on this, so you got to verify the continuity, the differentiability, verify the y values are the same, then you can apply Rolle's theorem. And Rolle's theorem is stuff we've been doing a lot. Set derivatives equal to 0. That's the idea. Okay, let's do number 10. It won't take us very long to do number 10. Okay, I give you this function right here. I graphed it on the calculator. I got 1 minus x. Okay, so is this function, the way I've got this is -1, that's 1. Are you continuous from -1 to 1? Are you differentiable?
No.
No, problem done. No Rolle's theorem. Okay, all right, can't use it, okay? So, and that's pretty easy to see. This is, this point right here, you're not going to have a horizontal tangent line. You can't make a defined tangent line at a cusp. I mean, you can't just, you can orient it different ways. You can't narrow it down to one thing. All right, let's do this last problem on the next page and we'll take a break here. Okay, so with this one, we've got this function. We're going to look at an arbitrary interval -a to a. Okay, and a lot of these problems, you're not going to be familiar with the graphs. I'm familiar with this because of statistics. This is a very famous curve. You know what we call this? If you've ever taken statistics, you call it the bell-shaped curve. Okay, so it's basically the bell-shaped curve is the graph of e to the -x squared. So I went ahead and put this on the calculator, and I think I did this like from 5 to -5, like this. So what we're going to do on this is we're going to see if we can use Rolle's theorem on this. And a to a just means like 5 to -5, 1 to -1, you know, equal and opposite values like this. So does it look like we're continuous?
Yes.
Yeah, and the thing is, x can be anything in this problem. Okay? I mean, an exponent can be any real number. So no matter what you plug in for x, you're going to get an answer. So there's no place where that's undefined. Okay? Is it differentiable? Yeah, okay. You can take the derivative of e to the -x squared. There's not going to be any place where that derivative is undefined. Okay, we'll do that derivative in a minute. Now, what we're going to do is we're going to do f of -a and f of a, and we're going to verify if they're the same or not. Okay, so we're just going to go, and this actually, I guess, should be h of a. So h of -a is going to be e to the negative and just replace the x with a. So you'll get that. So that's going to be e to the -a squared. Okay. Then if you do h of positive a, you're going to get e to the -a squared, so you get the same thing. Okay, so they're both equal to the same thing, even though it's just a variable expression. That means that Rolle's theorem applies to that. So we've double-checked every little issue that we have to have then. Okay? Now you can see by my graph, you can see where that point is, but you know, we want to use calculus to verify. So it looks like at x equals 0, you're going to have a horizontal tangent line. Okay? So what we're going to do now is we're going to go ahead and do our derivative, h prime of x. Okay, so talk out how this goes. If you do a derivative of e to a power, in words, what do? It's self times derivative of the exponent by chain rule. So it's going to be itself, don't change it, then multiply by the derivative of negative x squared. See, that's the chain rule. Okay, so you're going to have e to the negative x squared times, then this derivative right here is going to be negative 2x. Okay, and I'm going to write this as negative 2x e to the negative x squared like that. Now what we're going to do is we're going to set that equal to 0 and we're going to solve. Okay, and it's already in a factored form. So you got negative 2x. I'm going to put parentheses just to emphasize this. Okay, it's already factored. You can think of that as factored. So what do? You take this factor, negative 2x equals 0, solve it. Then you take the other factor, e to the negative x squared equals 0, and solve that. So this one clearly is going to give x equals 0. Okay, that's the one graphically we can tell visually that's right. Now how about this one? Can you think of a number that you raise e to that would give you 0? There isn't such a thing. If you take a number to any power, you always get a positive number. So it's basically e to any power is going to be positive. Always will. Even if it's e to the negative 1, that's still positive. Even if it's e to the negative million, that's still positive, right? It's never 0. So that has no solution. So then this would be your answer to your problem like that. Okay? Now visually on these things, I welcome you when you're looking at homework and stuff to look at your graphs on your graphing calculator because it'll help you understand stuff. But ultimately, we want to do the calculus. I mean, that one's easy to see what the answer is in your head with the technology, but you want to know how to do the calculus to get that answer. Okay? All right, so just to summarize here, and then I'll give you a break here. Rolle's theorem, there's 3 things. What are they? Must be continuous on the interval, must be differentiable on the interval, and then they have to have the same y values right there. Then when you verify that, all it is a matter of taking the derivative, setting it to 0, and finding at least that 1 point, because it's guaranteed to be there. Okay? Does that make sense? Okay? All right, so let's go ahead and take about a 10-minute break. Okay, so next thing we're going to look at is mean value theorem, which has some similarity to Rolle's theorem. It's related. The idea on the mean value theorem is you have to have a continuous function. It's on a closed interval and it's got to be differentiable, just like Rolle's theorem. And then this says there's 1 point that's in this interval such that the derivative is equal to this. Now what does that f of b minus f of a over b minus a look like to you? That's like a slope formula, right? So it's really what it's doing is it's given an average rate of change. So what's going on this problem, you can kind of look at this diagram. This is a good way to explain this. The difference between the mean value theorem and Rolle's theorem is the endpoints of your interval do not have to have the same y value. Okay, so I've got f of a over here and I've got f of b over here. They're different. They have different y values. So the idea is if you found the slope, which is the average rate of change, you might make a note here. I think I'd do this, the average rate of change. Okay, if you find the average rate of change, which is really what that's doing again, is that is the slope of the secant line, like we learned. Well then, according to the mean value theorem, as long as your function is differentiable, okay, and continuous in that interval, then you should be able to find a point where the slope of that tangent line is the same as the average rate of change. Does that make sense? Okay. So the idea is if you had, any 2 points like A and B, and it doesn't matter now whether they have the same y value or not. Okay. You could basically go through, you would have the slope of the secant line. That's going to have some defined slope m, and then your curve, as long as it's continuous or something like that, you should be able to find at least 1 point where the tangent line would be the same as the average rate of change. In this case, on this example, well, you'd have a point there. That looks like that would kind of have the same slope. Looks like this would have the same slope, and it looks like that would. So in this case, there's 3 places on that interval where they're the same. Does that make sense? Okay. That's what the mean value theorem essentially is saying, is find that point in that interval that's the same as the average rate of change. The average rate of change is the slope of the secant line. Okay. All right, so let's do a few problems on the next page. And we're going to start with, we're going to have this function, a polynomial function. So we're going to determine whether it satisfies the conditions of the mean value theorem on this interval. All right, so here's what you got to basically do on this is you got to verify these 2 things. Okay, is this function continuous? Okay, it always is because it's a polynomial function. It's a cubic function. Is it differentiable? And again, it's a polynomial, so you don't worry about sharp points and places where it's undefined like that. So those are the 2 things that you have to satisfy. The y values do not have to be the same. It doesn't make any difference. So what we're going to go ahead and do on this is we're going to crunch out, and I went ahead and just did the graph on here. So like here's -2 right here. Here's 2 here. So we're going to figure out what the function values are, and let's do this. We can use our calculator to help a little bit. Over at the side, I'm just going to do f of -2. So that means I'm just going to plug in to this function. So I'm going to do 2 times -2 to the third minus 3 times -2 plus 1. So we need to get that value. We've got to get 2 points. So that's 2 times -8 plus 6 plus 1. So that's -16 plus 6 plus 1. So that's -10 plus 1, so that's -9. So that's going to give us a point, -2, -9. That actually would be kind of what that point is on the graph. If you extended that graph down further, that's what you would find. Okay. Then we want to go ahead and find f of 2. And do that. So we're going to plug 2 into the function. So the function again is 2x cubed minus 3x plus 1. So I'm going to replace x with 2. Okay, so what I'm going to have is 2 times 8 minus 6 plus 1. That's equal to 16 minus 6 plus 1. So that's going to be 11. Okay, so that's just arithmetic. I did that pretty quick. Arithmetic, you can use your calculator to help a little bit if you want to on your homework. So anyway, those are the points. So this point up here, somewhere up here, you're going to have a point 211. Somewhere down here, you're going to have a point -2, -9. Okay, like that. So you're going to end up having like kind of a secant line slope like that that we need to find. Now, if you look at this graph, it looks like maybe up in here somewhere, you might have a tangent line that's the same. What do you think? And maybe down here, you might also have a place where the tangent line is the same. So we're going to use calculus methods to figure that out. So we're going to go ahead and just find the slope between these 2 points. So we're going to just do 11, or you can do this backwards. We go -9 minus 11 over -2 minus 2. So that's just the slope formula. You're finding the slope of a secant line. So that's going to be -20 over -4, so that's equal to 5. Okay, so the slope of this secant line is going to be equal to 5. Okay, so if we're going to find the points that satisfy the mean value theorem, what you want to do is you want to take the first derivative of this function, which is an easy one, set it equal to 5, and solve that equation. So it's probably quadratic. So our derivative is 6x to the second minus 3, like that. Now you're going to set that equal to 5. Now, like on Rolle's theorem, we set it equal to 0, because Rolle's theorem guaranteed that we'd have a place where the derivative is 0. This now guarantees a place where the derivative is equal to the secant line. So we just say 6x squared minus 3 equals 5. Okay, this is just going to be 6x to the second equals 5 plus 3. So that 6x squared is equal to 8. And this is kind of nice. We don't have to factor anything on this one. So we can divide by 6. We get x squared, and 8 over 6 reduces to 4/3. And then what do? We do the square root of both sides. Okay, and then I'm going to do something on the calculator on this to kind of take through a couple things. Now, don't forget you have a plus or minus, so you would have x equals plus or minus 2 over the square root of 3. Okay, and if you rationalize that, and you don't necessarily have to, you would get plus or minus 2 root 3 over 3 would be the two places where this exists. Okay, now I want to do this a little bit on the calculator. So what I've done, I did a lot of arithmetic on this. I had to find the function values that I did over here, and I had to find the slope of the secant line. So does the slope of the secant line, does that make sense to everybody? I crunched that arithmetic fast. I agree with that. You will too on this kind of a problem. You can double check it on the calculator if you want to. What I want to recommend that you do on some of these problems is work with your calculator as a checking tool and an understanding tool. So what I'm going to do is, if you want to do this with me, let's just put in 2x to the third and minus 3x plus 1. And I'm going to do this window like I've got on your handout, although I'm going to change that a little bit. I'm going to do negative 2 to 2 because that's the interval you were specified. Let's make this go down to, since that y value is 11 and negative 9, let's y max make it 15, y minimum maybe make it negative 15, and you can scale by 1 if you want to like that. So what I wanted to show you is how you can pretty well check everything on your graphing calculator on this problem. So if you wanted to check your endpoints, and if you want to speed your work up on your homework, I don't mind you doing this. You could bypass all this arithmetic right here, just do this real quick. Trace at negative 2. What pops out? Negative 9 does. See, that'll speed you up. Then you can trace at 2. That'll give you 11. So see, that was fast, wasn't it? That saves you a bunch of time, and you're going to be accurate if you do it that way. Now what you want to do is look at your points. Okay, so if you traced at, one of our answers is 2 times the square root of 3 over 3. Let's see, that doesn't look quite, yeah, that's fine. Okay, that looks like that would be visually one of the places where the derivative might be the same as the derivative of the secant line. Can you guys see that okay, kind of? Think of your secant line as those 2 points being joined. Think of the slope of the tangent line. That looks visually like it's probably right. Then you could also trace at negative 2 times the square root of 3, divide by 3, and then that should give you a point kind of over in here somewhere. So that visually doesn't really verify it, but at least it helps you see that you're in the right area. Does that make any sense? Okay. All right, so that would be one thing you could do is to double check some of this on a calculator. Okay, so that would be a pretty good example of how the mean value theorem is an exercise to help you learn it primarily. The mean value theorem shows up in a lot of areas in calculus, so it's a real important thing to learn something about. Okay, let's do a few other things on this. So with this one, we first of all want to apply the mean value theorem on this. So we've got the ln of 2x from 1 to e. Now I went ahead and just graphed it from, and this is 1 here. I made my graph go 1 to e like that. And then I made my max here go up to 2. So I kind of made that go like that. All right. So you can tell it's continuous. A natural logarithm function, the way logarithms tend to go is they go like this. You have a point 1, 0, and logarithms are going to be continuous and differentiable on the values where they're defined. Okay, so that one's going to be continuous. So what we're looking for again on this is we're looking for the mean value theorem basically says you could find a slope of that secant line. Okay, we can find that slope, and there should be one place where the slope of the tangent line is going to be the same. So can you see kind of a point that would give that? Well, it's got to be in there somewhere. It's probably going to be somewhere around here where you're going to have a tangent line that slope looks like it's the same as a secant line. That's what you need to understand. Does that make sense? Okay, there's at least 1 point. There's probably just one answer to this one. All right, so what we're going to do is we're going to do the first derivative. Okay, now we're doing a logarithm. So when you do a derivative of a logarithm, what do? In words. 1 over the function times the derivative of the function. Good. So you're going to say 1 over 2x times the derivative of 2x. So I'm going to write that as d dx of 2x. And you can do this in your head if you want to. So that's 1 over 2x times 2, right? 2's cross out. So that means your first derivative, f prime of x, is going to be 1 over x. Okay, like that. So what we got to do on this now is we got to set that equal to the slope of the secant line. So the other thing I need to do is I need to find the slope of the secant line. So we need to get 2 points to do that. So we're going to look at the interval 1 to e, and we're going to plug in, and we're going to do this analytically without our calculator. So we're going to do really f of 1, which is going to be the ln of 2 times 1. Okay, just go to your function, replace x with 1, so you're going to get ln of 2, okay? Okay? That or leave. I don't want to see it ever a cell phone on your desk, okay? Got a paper? Start writing, okay? All right. All right, so this is going to be ln of 2, all right? Now what we got is f of e, so we're going to do ln of 2e like that. So we got that. So what you have now is you got 2 points, okay? You got a point 1, ln 2, then you also got a point which is e, and ln of 2e like that. Okay, now we're going to find the average rate of change on that, and we're going to set the derivative equal to that then. Okay, so I've got to find the y values of those endpoints of the interval, which I've done, and I've written those in an exact form basically on that. All right, so what I'm going to do is I'm going to find the slope. Okay, and what I'm doing is I'm really finding the average rate of change. Okay, so what am I going to do? I'm going to subtract those two. So I got ln 2e minus ln 2 over e minus 1, like that. Now there isn't going to be too much that you can do with that. We could go through and get a decimal value on that if we want to, but we're going to get an exact value on this problem, typically is what we're going to do. So we have ln 2e minus ln 2 over e minus 1. Does that make sense? Okay, that's the average rate of change. So what you got to do is you got to work with this thing, and you got to work with this thing. Okay, now you're going to get into some algebra. There's a temptation to just want to change everything to decimals, but we want to get precise answers, typically. Okay, so here's what you do to finish up a problem. You say 1 over x, which is your derivative, is equal to ln 2e minus ln 2 all over e minus 1, like that. All right, now how are you going to solve an equation like that? Probably, you can even do the reciprocal of both sides. That's a proportion. So you can cross multiply. You can also just do the reciprocal of both sides if you want to. Because what you're going to have really is 1 times e minus 1 is e minus 1. Then you're going to have x times ln 2e minus ln of 2. Okay, then if you're going to solve by x, you're going to have to divide by that quantity anyway. So you're going to get x equals e minus 1 over ln of 2e minus ln of 2. All right, so that would be the exact answer right there. Now, and if you did that in terms of decimals, of course, you'd just get your calculator out, and that would be the value, the exact value on x, whatever it is. That's going to be the exact value where the slope of that tangent line is equal to the average rate of change. Okay? Now, here's something to think about on this. Okay, think about you're driving in your car, and you're going from 0 to whatever miles per hour. There would be an average velocity in that range, wouldn't there? Does it make sense that there's some point in time where the instantaneous velocity would be the same as the average velocity? That's what the mean value theorem says. Another way to look at it is, what if we averaged all your test scores for the last test? Okay, there's some value, maybe nobody made it, that would be equal to the average, right? It's the same thing. Okay, so that's what the mean value theorem is basically saying, is there's some point where the instantaneous rate of change, which is represented by a tangent line, is equal to the average rate of change. Does that make any sense? Okay, right? Now, so you get into some weird looking answers on these when you do some of these. Okay, so let's go to this next one here. Okay, so here is a 3 sine of 2x, okay, like that. And let's see, first of all, we're continuous. Why? Because it's a sine. Okay, differentiable? Yeah, it's a sine wave. There's no sharp points on a sine wave, even though it's got a period change. It doesn't matter. Okay, so what we're going to go ahead and do on this, on the mean value theorem, you want to do the derivative and you want to evaluate these endpoints. So we're going to go ahead and evaluate these endpoints first. So I'm just going to do this. You can do this wherever you want to. You should have room. So we're going to do f of 0. Okay, so we're going to do 3 sine of 2 times 0. So that's going to be 3 sine of 0. Okay, now I hope you don't have to go grab your calculator for sine of 0. The point on this unit circle is 1, 0, so what is the sine?
0.
That's the y value, right? Okay, so that's going to be 0. Okay, so we have a point 0, 0. Okay, and I've already put the graph on there, so you can tell pretty visually that's right. You can verify on the calculator. Now we want to do pi over 4, so we want to do f of pi over 4. So we're doing 3 sine of 2 times pi over 4. And this is unit circle stuff. So you're going to have sine and then 2/4, of course, is a half. So you got sine of pi over 2. Okay, pi over 2 is the point 0, 1. So what's the value of the sine at pi over 2? 1. Okay, so that's 3 times 1. So you got a point 3. Okay, so that means this point right here is the point pi over 4, 3 like that. Now, of course, what we're going to be doing on this problem primarily is we're just going to be finding a slope of that secant line, kind of like this. Okay, so you got that secant line in there, kind of like it. Boy, look at me. How cool is that? Okay, whoa, okay. So, can you see a point somewhere in here where the instantaneous rate of change would be the same as the slope of that line? Yeah, maybe kind of in here somewhere or something you would have a tangent line doing that. So what we need to do is we need to go ahead and finish. We've got our points now, so we need to just find the slope, or we need to find average rate of change. Okay, so we have these 2 points. We're going to do 3 minus 0, rise over run, really. Then pi over 4 minus 0 like that. So that's going to be 3 over pi over 4. So that's going to be 3 divided by pi over 4. And then you can do the reciprocal of that. So that's going to be 3 times 4 over pi. So that looks like that average rate of change is 12 over pi. Don't get decimals, just get precise answers. That's what we're typically after on that. So we did the slope formula. So that part right there should be okay, I would think. And then, of course, I had to do the trig. So is there any questions so far? Okay. All right, now what do? We got to do the derivative next here. So this is an important thing because we've got the average rate of change. So now we've got to work on the derivative. Okay, so we have 3 as a constant times the sine of x. So how do you do the derivative of the sine of something in words?
The derivative.
Cosine of that something times the derivative of that something, right? So it's going to be cosine of 2x times the derivative of 2x, which is 2. Okay, that's a chain rule thing, which is going to keep popping up. So we have 6 cosine of 2x like that. Okay, so now what we're going to do is you're going to set this equal to the average rate of change. You're trying to find where the instantaneous rate of change is equal to the average rate of change. So the equation we're going to work with is 6 cosine of 2x is equal to 12 over pi. Okay, like that. All right, there's a couple of things that you'd want to do on this. One thing that you'd want to do is you would probably want to multiply both sides by 1/6, or divide by 6 is the same thing. That would cross this out. That would leave the cosine of 2x. And see, this 12 over 6 divides out, so you have is equal to 2 over pi. Like that. So you got to figure out where such a thing happens. Okay, by solving that equation. All right. Now it's trig review time. Okay, now this is something that you learn in a trig class. You really do. What you do in this case is anytime you have like a sine or a cosine of something other than x, the best approach, and see I've got that cosine isolated, is you want to take the inverse cosine of both sides of this equation. Now you guys did this in trig. I know you did. If you took my class, I know I taught it to you. Okay, does that look familiar? Okay, all right, because we're not going to have to do too much with this problem. Okay, what is the value of the left side? The inverse cosine of the cosine of 2x. What is that? 2x. Okay, that's why we did it. Okay, and then this is equal to the inverse cosine of 2 over pi. And then what you would do is you would just multiply both sides by a half. So you would end up having x is equal to 1/2 inverse cosine of 2 over pi. And that would be your solution. You could check that and verify that graphically. That's the exact solution right there. Otherwise, you just got to get your calculator out, do the inverse cosine of 2 over pi, and get an approximate answer. I'm going to go ahead and do this on this problem because I want to see if it kind of interpret, what in the world did I just do? Okay, there we go. So if I was to go through, I'd put it in like this. I could say 0.5, and then I could do the inverse cosine. I'm going to make sure I'm in radians on this because I want a real number answer on this. So I would just go 0.5 inverse cosine of 2 over pi. And I want to do this just to see visually if it makes sense on the graph. So that's about 0.44. So let's just round that off like that. Okay. Now if you look at the point, now I think the way I had this worked out, it's a little hard to tell on here. This was going from 0, this was going out, this is right here is 0.78 on this. So 1, 2, 3, 4, right in here somewhere. Does that look like it might be a good place where the tangent line's equal to the average rate of change? Okay, that looks pretty good. Okay.
How do you know the inverse cosine of cosine 2x? So totally was 2x.
Okay, that's a fundamental thing that you learned in trig. It's an easy thing to forget. But if you do an inverse, you're undoing the operation. So whatever is there, you just get it back. It's no different than doing like if you square a square root, you get x back. It's the same thing.
The other side carries that.
Right, you have to do that operation to both sides. That's a type of equation you learn how to do in trig. It's a real easy one to forget about though. Okay, so that would be the exact answer, and then you could round that off like that. Okay, so just a couple more things I want to go through to finish up. The thing that you're going to get into here is not as much the calculus as the arithmetic. Okay, to me, this is what I help students mostly with these kind of problems, is on the arithmetic and stuff. Okay, all right, let's look at this now. This says, now this one's a pretty simple one to do. All right, so what you have is these are your endpoints right here. So if you were going to go through and look at the mean value theorem, basically what I would be doing on this is you would want to look at the average rate of change. So I'm going to draw like a secant line through that, the best I can, kind of like that. So that's a fairly good secant line right there. So how many places do you think on this graph would have a slope of a tangent line equal to that slope of that secant line?
3.
Probably 3. Good, okay. You would probably find that somewhere in here, the tangent line would be about the same, right? Somewhere in here, and it's an estimation, and then maybe somewhere in there. So it looks like about 3 places. Okay, now this is estimating, so there's the right way to do it. That's obviously with the calculus, but it would look like maybe around -3, close to -3, it doesn't matter, close to -1, and then fairly close to 2, somewhere in there, give or take some decimals like that. Okay, so that's the mean value theorem. That's what it's saying. So if we got that down, what are the 2 conditions that have to be true for the mean value theorem to work? Differentiability and continuity on the interval. Okay, the y values do not have to be the same like they do on Rolle's theorem. Okay, all right, now there's a couple of things I want to just finish up, then we're going to get into the next section. This is, I'm not going to do much with this. These things are pretty obvious, I would think. The zero derivative implies constant functions. What this is saying is if you're differentiable and the first derivative is 0, then all points are going to be on a constant function. Okay, so it says f is differentiable, and the key thing is that the derivative is 0 at all points. If the derivative is always 0 on an interval, what would the function have to look like? It'd have to look like that, right? Okay, so all that's really saying is this. It's pretty obvious. It's not a hard thing to understand. It's just, hey, if you got here's A, here's B, there's your interval like that. If the derivative is always 0, I'll just say f prime of x equals 0. There isn't any other way to draw it, is there? Right? Okay, you're continuous, you're differentiable on that interval. It's got to be that way. All right? Some of this stuff will be kind of important when we get into integration. What this next theorem right here is saying is it's saying if you have 2 functions that have equal derivatives, so this is just saying f prime of x and g prime of x are equal to each other, okay? Then it's going to say that basically these 2 functions are going to differ by a constant. And it's pretty easy to explain this with examples. So I'm going to try to do it this way. It just means if 2 functions have the same derivative, then they're only off by a constant. So here's an example. I'll see if you can give me an example on this. Let's say f of x is equal to e to the x plus 2. What's the derivative? E to the x, right? Can you give me a function, g of x, that would have the same derivative? There you go, e to the x plus 5. What's the difference? It's off by a constant, right? That's the constant that's made the function different. Okay, that's a good example. How about this one? What if I gave f of x equals 2x minus 3? What's the derivative? 2. Now, can you give me another function that has a derivative of 2 that's off by a constant? 2x plus or whatever. Okay, so you get the idea. Okay. All right, now the thing about that is would be if their derivatives are the same for all the intervals on that interval, then they would differ by a constant. Okay, and that would be the idea. Okay, and let's see. The last thing I wanted to kind of look at here is we've already talked about increasing and decreasing, so we know what that means. Increasing, we said, would be on an interval. Those would be at places where the derivative is positive. And we said decreasing is going to be basically the places where your derivative is negative. So this just says you have a continuous function. It's differentiable on all points on an interval. So if f prime of x is greater than 0, then you're increasing, and if f prime of x is negative or decreasing. So we've talked about that, and we've done some problems on that. All right, what this number 26, I took this out of the book, and you're given these functions. So what you want to try to do is try to figure out, without doing derivatives, which ones you think would have the same derivative. And the key thing is, they got to be off by a constant. Whatever you're differentiating has to be off by a constant. So to pair these things up, which ones do you think would have the same derivative? Yeah, okay, it looks like if you think about this, if you did f of x equals ln of x, well, we're not supposed to do a derivative, but if you did, what would you have? 1 over x. Okay, then g of x is the x and the 2x are off by a constant, right? Okay, so what you'd have is you'd have g prime of x would be what? 1 over the function times the derivative of the function, so they'd have the same thing, okay? So it's the 2x that's off by a constant. It doesn't necessarily have to be ln of x and 2ln of x, because those don't have the same derivative, okay? But it's the fact that the argument is off by the constant that made those work that way. Then you have h of x equals ln of x squared. What's its derivative? 1 over the function, right, times the derivative of the function, okay? And then if you did p of x, okay, p of x is equal to ln of 10x to the second. Again, the arguments are off by a constant, and that's what's going to make them have the same derivative on this logarithm function. So p prime of x is going to be 1 over 10x to the second. The derivative of 10x to the second is going to be 20x. And they're going to have the same derivative if you go through and simplify. Okay, does that make sense? So the idea is on these logarithms, it's the argument that's off by a constant. That's how you would visually know that it has the same derivative. Okay. Okay, so this last page here, real simple, just want to remind you of this. This says that we're interested on the interval 1 to 3. Open interval 1 to 3. Okay, it says at which find the slope of the tangent line where it would equal the average rate of change. Now, if you look at this and this, what do you think the average rate of change is going to be on this problem? Looks like 0, doesn't it? Looks like if you did a secant line through those 2 points, you're going to get the average rate of change is equal to 0. So is there a point that would also have a derivative of 0 between 1 and 3? No. Okay, so the mean value theorem does not apply. How come? There you go, it's not differentiable. Okay, so that would be the idea. Okay, you can't find a value on there that also has a derivative equal to 0 because it doesn't satisfy the conditions of the mean value theorem. Okay, all right, does that make sense? So remember, you had to be continuous on the interval and differentiable. Then the mean value theorem is guaranteed to apply. It's an absolute guarantee, regardless of what the function is. Okay? Okay, so I'm going to go ahead now, and I'm going to move on a little bit to